there we go. Glad to hear it. So, I feel like a one-man band. I had to hit a whole bunch of buttons. So, you know the one-man band, you like has a guy with a bass drum on his back, you click your heels, makes it do that thing, hit the hi-hat with a finger twitch or something like that. You know, that's what I feel like today. Because we're going to be switching back and forth between our little iPad view and coding today. So, all right. Hope everyone had a great time fitting all of your functions for the homework that was due last week. Next homework, yeah, I just look at all this beautiful, like the smiling faces, like, oh, I look back on it so fondly, okay, right? And we coded up forward neural nets, right? So we have neural nets. Start here. So what's today's date? 2026-02 and the 19th of the Common Era, not BCE, all right? Here. So what have we done so far? So we learned how to fit models that we have built by hand. I'll put hands in quotes because I'm sure 19th century farmers would be like, what are you talking about? Till the soil by myself, my physical hand. Type it on a magic device, right? So meaning that we coded up linear models, those polynomial models, and neural nets from scratch. And when I say from scratch, what I mean is that you don't use anything more complicated than NumPy. You don't need anything more complicated than arrays, okay? So like using NumPy. You know, that means when we did a neural net, we're doing a neural network model. Okay, we would have to say, hey, here is our neuron, goes into these other neurons, then it goes into a bunch of other neurons in another layer, and I'm going to connect all those layers. A fully connected, dense network of layers. Oh fun, oh joy. I think I got all the connections there. You have some output, right? And by hand, we did back propagation, where we went from one node to one node to one node to the end. What does back propagation give you, friends? What do you get out of a back propagation? What's that? Gradients. And I didn't have to rhyme this time. Isn't that nice? Can you hear me okay on the stream? I imagine I can. I can see the levels. So, all right. We did that by hand. And guess what, grad students? You get to do this by hand. Aren't you excited? It's all right. It's all right. It's okay. It's the exact same formula we did before, okay? It's just a little, you know, every time we said, that's a matrix multiplication. Ignore that. Now you don't ignore that. See? Look, there's just a twinge of a smile off of you. Brennicarian smile, just a corner of a smile off the end of that. That's will be part of homework 2 for the grad student, okay? The undergrads want to do that too? No, I won't put that on you. That's a me decision. I love the nod I got off of you, right? So that's what we did all that by hand. Well, guess what? You all had to do it. I think it's an important experience because you got to know what goes into it. But do you want to do that every time? You want to try a new neural network? No. Especially when you have different types of neural networks. You'll have, and right now this here is a feed forward. You could also consider it a sequential neural net, right? But you could also have recurrent neural networks. That's when the neuron goes back onto itself. That sort of encodes time history from previous versions of the neural net. It's all kinds of cool, nifty ways you can include different types of neural networks. There are also different types of layers, okay? We talked about these fully connected layers in a multi-layer perceptron, okay? We also talked about these little batch normalization neural nets. You add those as layers, right? There are also things called convolutional layers. They're really cool. I mean, right now, we're doing things that only I find fun, which is fit that curve. And I say, oh, I'm so excited I fit. But you're going to do things that are maybe slightly more exciting to you, such as classifying images, right? You can use these same exact ideas, just the layers might change. You might have something that's called a convolutional layer. It's a different kind of layer. You can still do back propagation from it. Guess what? You still got to do gradient descent with it. All right? Because you have all of this common functionality that you need across all these different types of neural nets, people have built entire frameworks, entire libraries. Okay? So libraries for building and training neural networks. Okay? A very common one you might hear is called PyTorch. The Pi stands for Python, which you're all coding in. The torch is, right? Okay? But it's a library for setting up, building, and training neural networks. Okay? There's another one called TensorFlow. Now, why tensor? Anyone remember what a tensor means? We talked about it briefly in class, or if you took in tensor mathematics, you might know the answer already. What is a tensor? It's like a 3D matrix. Okay? We know like a 1D matrix is a vector. 2D matrix is a matrix. 3D matrix we'll call a tensor. Well, actually, if you want to be cool, actually, let me say it this way. If you want to sound pretentious, okay, you can call everything from a vector to a matrix to a 3D matrix or an ND matrix, call it a tensor. Like, oh, I'm just doing tensor math. That's a vector. That's a 1D tensor, friend. Okay? Right? You can sound really pretentious really fast, right? But TensorFlow is another example of a library. This is what we'll be using in class. Okay? TensorFlow. Now, TensorFlow, very usable on its own right. You can use the library directly, okay? People who are in industry absolutely do. But for people who are new to Python and TensorFlow, people said, hey, let's have an easier way to interface with TensorFlow. So an easier interface, we call it an API. So it has an API. So that way you can set things up easier. Okay? That's called Keras. Right? The reason we're using it because it's easy. Many of you, this is your first experience with neural nets. First time for everything, right? Okay. And it builds in a lot of the functionality. It has a lot of the all the functionality of TensorFlow, but it kind of makes it simple, okay? But if you want to get into the weeds of advanced neural networks and things, you might want to learn how to use TensorFlow directly. Keras is just a way to talk to TensorFlow, okay? How simple or complicated does it get? Well, let's find out. We're going to go through an example today, okay? Assuming that I can use these 3 monitor setups, okay? All right? So, pull up Google Colab, make sure. Okay. Window. No, you can't see anything yet. See if this works. Okay. Fair enough. There we go. There is my, this is Google Colab, so you can go to colab.research.google.com like we've all been doing. Let's make a new notebook. Okay? And that act of making a neural net that fits a curve, we're going to go through that today, but using the language of the API of Keras. Okay? Now, if you want to know how to do more with Keras, we'll cover as much as we can in a lecture. Okay? But a lot of it, you can just go to Keras's webpage, look at the documentation. You might say, hey, I want a different type of activation function. And so you can just change it, right? And it'll give you the options. Show you a few options today that are very similar to what we covered in class so far. So I'm going to go onto my computer, sit down so I'm not hunching. I'm going to create a new notebook. People see this? Okay, I'm going to try to zoom in a little bit so you can see a little easier. Okay. Can I zoom in? Can I zoom in? Oh, I can. Well, I kind of don't want to. Can people read that? If I say 1 + 1, is that too small? Okay, let's zoom. Let's see if we can change the view. It's also trying to do 1 plus 1. What's the worst that could be? Okay, 2. It got it. It got it. Let's see. Let's try to zoom in a touch. View. What? View. Zoom in. View. Zoom. My hotkeys. Okay. Haha. There we go. That's a little easier to see. Okay, that makes everyone. Okay, is that okay? Thank you. All right. We can do math. Good start. Good start. Okay. So our goal here is we're going to try to our goal is to fit a neural network to a predefined curve. So we're going to try to do some kind of fancy sine wave big thingamajig. Okay? There's our input, there's our output. And we want to see if we can get a neural network that isn't made of sine waves to approximate this. All right? If we get it to approximate this, heck, maybe we can get it to approximate anything. Okay? And we're going to make it so it is built. We're going to build a feed-forward sequential neural network, NN, with tan H hyperbolic tangent activations. Okay. And a final linear layer. Okay. That's what we're going to do. So let's start with how we know how to build this. Okay, let's make a new library. Let's call it first Keras. Okay. A new notebook. All right. Let's make a little text at the top. And it's like, you know, the first Keras implementation of a neural network. All right. Goal, and also by me and all my friends. It's all. I wish that was Latin for friends, but okay. So when we are starting with a new piece of code, you have to know what libraries you want to put in. So we're still going to be using our good old friend NumPy. So we want to say import NumPy as NP. Aliasing it as NP. Same deal, right? Good. I still like plotting things. Are you fans of plotting things still? Which point we'll say import matplotlib.pyplot as PLT. Now we can plot things, all right? That all still works. Great. Now, we also want to use Keras. So we're going to say import TensorFlow as TF. We need TensorFlow. Let's see if that runs. It work. It's executing. It's importing. 2, 3, 4. Good here, by the way. Shockingly. Okay. Oh, look. Okay, didn't throw an error. That's good. Because it's possible that Google Colab didn't know where to find TensorFlow. Like, you could make your own library. What's your name? What? Emily? You could have Emily Flow. You can make it on your own computer, but that doesn't mean that it has access to it. So you might have to install it. So there's a pip. We might have to do a pip install. Clearly we don't, because it's able to find TensorFlow. We don't just need TensorFlow, we need Keras. So we would write out, we want to import. So from TensorFlow is what we say, from TensorFlow. This is bad for my back. I'm going to do this. I'd sleep on bamboo. That's not good. You'll see. You'll see if you watch. It's TensorFlow. As you get older, it gets harder to do that. Let's see. Import from TensorFlow, import Keras. This should give us access to all the functionality of Keras. Seems to still want to run. That's good. Which means we don't have to install it. Okay? But if you needed to, I'm going to put this up at the top, but we won't run it. What you would want to say is that if you don't have something, you would say exclamation point pip install. Don't run this TensorFlow. You can, but TensorFlow. Okay? It would run that, and then it would install it, and then you could use it. It would know where to look for in the pip library where to find TensorFlow. That's what you could put. I'm going to delete it. Gesundheit. That felt like it came from the rooftops. All right, goodbye. Got rid of that. Girl, bye. All right, so now we're going to go on. Now, okay. So now we have access to, all right? Now let's try to create this function that we want to define, that we want to follow, okay? So my student DJ, who's actually the TA for the other class, made a fun little function, okay? So what we're going to do is we're going to define the training data, okay? And for this, we're going to use just good old NumPy arrays, you know, lists of arrays all in a row, okay? List of numbers all in a row. So we will say, we'll call this xtrain, okay? And it's equal to NP, and we're just going to get a linear spacing of points across a range, for which we will use space. L.ln space, okay? And this is going to be like a sine wave. So we're going to do like minus 2 pi to positive 2 pi. So we're going to say minus 2. Pi, unlike in MATLAB, is not just built in to Python. You have to say np.pi. It's inside of NumPy. Then we'll do the positive 2 pi. So 2 times np.pi. So we have access to pi. And let's make, I don't know, 10,000 points. 10,000 points. Why not? Okay. Every once in a while, I just rerun the block, make sure I haven't made any mistakes. Okay. That's our x data. Those are the training points that we're going to want. Now we need the y data that we're going to predict. It's going to be that little sine wave thing. All right. So I'm going to create a function. I'm going to create a fitting function. Define a fitting function. Okay. So I'm going to create a function. I'm going to define it. Call it fit underscore fn for function. Why not? Takes in some value of x, colon, so that way you create things inside the function. And we're going to return. This is going to define our fancy function. So let's say return np dot sine, again, because it doesn't know what sine is until you tell it, of x plus 0.5 times np sine of 10 times x. So this is going to be a slow sine wave with a fast sine wave on top. Wiggle around for fun. The wigglier it is, maybe the harder it is to get the neural network to be. Okay. Meanwhile, because we're going to be using these tan H's. Because anyone with their hands draw a tan H for me in the audience. Go. Yes, you were first. That's good. Can anyone else do it? Fantastic. That was from your own perspectives, but I can mirror in my head. That's okay. The neck motion is not required, but appreciated. Thank you. All right? It's doing this, right? How do we get something that does this to do what this is going to do, which is, right? Magic is the answer. Oh, sorry. Machine learning is the answer. So let's take a look at what this function looks like. So let's get out of the function, but let's define our y data. So we'll call our y train is just going to be the fitting function, our fit function of our x train. Okay. Okay. Now let's plot that training data. See what it looks like. I'm drawing it, but it's possible your imaginations aren't so vivid that you can see what I'm talking about from my gesticulations. Okay, plot. Training data. So we're going to want to plot things. So plt.plot, our x data is going to be our x training data. Our y data is going to be y training data. And we'll just print it as a line. By default, it'll plot a line. So let's just put a little x label, plot plt.x label. Label x, plot y label, y, because we're just so clever at naming things. Great. Let's give it a title. Plot that title. This is our training data. And show it. Don't forget the plt.show, open close parentheses, because that's a function that has nothing that takes in. Let's run it. Running it. Hey, Mr. Wiggles right here. Yes. All your neck motions are seen by me, not the greater internet large. You're lucky. Okay. Right? So we turn a bunch of tan H's into that. I say yay. I say yes, we can. If we have enough of them in layers and enough layers, we can make it do that. Okay? So, anyone trouble so far? Just straight up NumPy and plotting, things we're all extremely good at this point. Okay? All right. So now we're actually going to define our neural network. Okay? We're going to define a feed-forward neural network. Okay? Particularly, we're going to make a sequential model. Okay? One layer after the next, after the next, after the next. There are lots of different types of models. You'll see we're going to be including in our code descriptors of things that we want. And you can find all kinds of different options, again, by looking at the documentation. That's just the online help, right? So we're going to create a model. So the way we say this is to say model is equal to Keras dot sequential. There was a game when I was a kid, it's called Mario Types, where you have to type to make it move forward and avoid the Goombas. I was terrible, as you can see. Yes, question. It has to be capital. At least I have not tried the lowercase. Okay? I would imagine it has to be capital because it's a function name. Okay? Now, let's run that. Didn't give an error. That's good. But inside of this open close, we can actually give additional arguments, inputs. So we can define things like a name. We can give it a name. We can say name is equal to, let's call it sine wave predictor. This is going to give a name to our model. Who here has ever dealt with object-oriented programming before? The answer is all of you have. You might not have known it. Okay? Whenever in the high-level languages like Python or MATLAB, and you say something dot something, meaning that here's this thing called Keras, and we wanted to do this thing called make a sequential thing, that's what we call object-oriented programming. Okay? Fancy name for it creates, well, there's something, it would be a class called Keras, and it has a whole bunch of functions and variables built in. So behind the scenes somewhere, when you say Keras.sequential, it's building what we call an object and stores it in a model. And that object can have stuff. It can have like a name, a variable name. So if I say, hey, look, that's the name, and I run that, it creates a name. Theoretically, let's see if this works. Let's say print model.name and see if that works. I didn't try this before. I'm winging it. It works. Okay? Right? So it's stored inside of model. If I were to create something called model2 and gave it a different name, I would say model2.name. It's stored in there. That's basic object-oriented programming. Now I could be like, I took a course in object-oriented programming. Dr. Hubicki, you said .name. Now I know everything. All right, well, not really. So that's what's happening here. So Keras is an object-oriented library, and that makes using it really simple. Because now we can use all of these built-in commands inside of Keras on this model. We created this object called a model, and we said it's a sequential type model. And now we can add neural network layers to the model. The documentation can read it. You can say, hey, take your model name, whatever you called it, say dot add. Open parenthesis. Okay. All right. And you can create layers. So here's the syntax for creating a layer. Okay. You can say, I want to create a layer. So Keras dot layers dot capital I input, capital L layer. Okay? So you can see inside of Keras, there's an class called layers. Inside of layers, there's something called an input layer. And you can define things about the input layer, like how many inputs do we have? How many inputs do we have, friends? 1. X. What comes out? Y. 1. All right? So you have to define the shape of that input layer. Okay, so here's the syntax for adding 1. Okay, open parenthesis. Okay, you want to say that the shape equals open parenthesis 1 comma. Okay, this will create a single input. All right, just syntax that you can follow and find online, or follow this example. Okay, actually. Can we, Nick, I'm gonna share this link. People can find it, okay? People can find it online. Restricted. Anyone with the link can view. Please don't edit. Okay. All right. I'm gonna send this away. I'm gonna send to you on Teams, Nick. If you could put on the YouTube. Hopefully it works. Hopefully it doesn't think you're a spammer. Okay. If I can get to work here, I'm gonna send this to you so we can get it out there. There's the link. See if that works there, Nick, and if so, put it in the chat on the. Right. Ooh. You wouldn't believe the keystrokes I'm hitting to make this happen. Okay. All right. Doesn't look that hard. And frankly, it shouldn't be. All right. We added an input layer. Let's run it. Anytime you add something new, hit run. See if it yells at you. It's not yelling at me. I like it. Okay? So let's add another layer. Okay? Right now we're at the input layer, right? That's the first thing. The one input. Now we want it to fan out into a bunch of neurons onto a new layer. And they're going to have hyperbolic tangents in it. Can everyone do this? Do the wave? Yes, it's not required. But thank you. You don't seem enthused. I just didn't want to force you to do the wave. Okay. All right. So, right. So we're going to add some layers of hyperbolic tangents. Okay. Model. So we're going to add a layer. So model.add. Add. Keras. .layers, and we're going to create what's called a dense layer, okay? Meaning that that's going to have all neurons, and there's going to be a weight line that's going to point to every one of those, okay? So a dense layer, okay? All right, and I'm going to add 20 neurons. I want 20 of them. So I'm going to say 20. And what kind of activation function do I want in them? What's the activation, friends? NH. So we're going to say activation equals NH. Okay. Let's see if that still runs. It does. Oh, thank goodness. Okay. I'm going to make another layer. I'm going to make it exactly the same. Literally, I'm just going to copy this. Okay. And then repeat. This is going to add another layer to the model. Okay. So I've got an input layer of 1. Got 2 hidden layers, we call them, in the middle, with 20 tan H's in them. They're all fully connected to each other. These are dense layers, so that first layer is connected to this one, and there's a weight going to every single combination. Okay? Now I'm going to do the output layer. Okay? I'm going to go to the output layer. So I'm going to say model.add. It's very similar to the other layers, okay? The only difference is I don't want this last layer being activated by a tan H, because the tan H is going to restrict it between 2 very small values. What I want to do instead is I want to just add together the outputs of all the previous layers, a linear combination. We call it a linear layer. So let's add that. So model.add Keras.layer, layers dot, it's technically a dense layer because we want a line coming from every single neuron to this last neuron. And it's just going to be 1 neuron. 1. But the activation is no longer tan H. The activation is now what we call linear. Boom. No errors yet. I like it. How are we doing on plenty of time? Granted, we started late. Who dropped frames? Oh, I'm a master of you. All right. So that's neat. But it's all pretty abstract. I'm just telling you, there's a layer here, there's a layer here, there's a layer here. Well, built into Keras are some really great features. I can say, hey, I want a summary of what that model looks like. So I can say model.summary. Open close parenthesis, because it's a function that I want to execute. And I run it. Hey, this model sine wave predictor got a dense layer of 20, a dense layer of 20, and then a dense layer of 1. Tells you how many parameters, by the way, there are for each layer. Let's look at just this. It says 40 parameters. Anyone want to guess what those parameters are? They're weights and biases. Okay, in fact, I'm going to go back to the board. Aha. Did that work? That is changing for you guys, right? Thank goodness. Okay. They're weights and biases. In fact, we had that one input, right? And then I have 10 layers, 4, 5, 6, 7, 8, 9, 10. 10. I count good. Okay? So it's going to be 10 weights. Pretend I'm doing 10 lines. And 10 biases. Holy Hannah. 20. Oh, wait. Yes. Sorry. Yes. I didn't draw. Yes. It's 20 neurons. 20 weights and 20 biases. Holy Hannah, 40. Does that make sense, or did I confuse the entire class? I made 20. I made 20. Right. I made 20. Right. Yeah. Sorry. 20 nodes. 20 neurons per layer. 20 weights, 20 biases is 40. And then for the next layer, I have 420. Where do those come from? Weights and biases, again, you're cheating, Angela. That's okay. You're right, but you are correct, right? You have to connect every one of the 20 neurons to 20 other neurons. That's 20 squared, with mathematicians will argue and tell you is 400. Then you have how many biases in that layer? 20 biases. Okay? Right? So that's what that's showing you. Makes sense? So it's giving you a summary of those layers. And those parameters, those are the things that we are going to optimize using gradient descent, but specifically fancier gradient descent. They have fancier gradient descent algorithms built in to Keras for us to use. That way you don't have to do that by hand, because we did gradient descent by hand, right? Right? Yeah, thank you. Sorry. I wanted a response there. Yeah, we did. Let's instead use other algorithms. We'll get to that in a second, okay? But that's our model. So now let's get to the point where we are let's optimize our model. Let's fit our model to our data. How do we do that? First, we need an optimizer. Okay. Okay. We need a cost or a loss function, right? So we can create an optimizer object using object-oriented programming. It's all built in. So we can say optimizer is equal to TensorFlow.keras.optimizers. And we're going to be using an optimizer, which is a subset of gradient descent or stochastic gradient descent, called Atom. Okay? We haven't talked about Atom yet, but it's just a fancier version of gradient descent, right? A key difference between Atom, one key difference between Atom and gradient descent is that gradient descent, you set your step size, right? You choose that step size. Choose a step size here of sorts, right? But one thing Atom is a little smarter about is it's saying, if this is going well, if I'm descending the gradient really well, I can change my step size adaptively. I can give it some momentum to go faster or slower. See if that helps converge. People have developed Atom for this momentum-based gradient descent. He's my Atom expert, so I'm looking at you. Thank you, Nick. So Atom can be smarter and faster about converging the model and training, right? Okay. So we can also set, instead of a step size, we call it a learning rate here. We can say open close learning underscore rate is equal to, and we'll set it to 0.001. I say that with malice and forethought. It's worked in the past for us for this problem. Okay? But who chooses it? We do. Right? We set our optimizer. Great. Remember we said what are the 4 components you need to know to set up a machine learning model? You need your data, your model. Hey, guess what? Your data. Your model. Your optimizer. And your loss function or your cost function. Same thing. Okay? Loss. Again, this is going to be another object. And guess what? That mean squared error that we keep typing over and over again, we're not the only ones to use that. And Keras knows that. So we're going to say Keras, so tf.keras.losses. It has a list of losses built in. We say, which one do we want? We want capital mean, capital squared, capital error. You can see it's also giving you sort of autocompletes here if you want to go with the mean squared logarithmic error. Why? Not today. What do we say to the god of logarithms? Not today. Okay, all right. So we got mean squared error, open close, yes, done. So this will create an object called loss that has a mean squared error in it. Okay? Let's run it to make sure no errors. Good. No problems. We got it. All right. Then one step you need to take before you actually run your training operation, you have to you have to compile your model. Okay? So we want to going to compile our model for fitting. So we just say model.compile because we want to tell it that this model has this particular optimizer and this particular loss. So right now we made a model object, we made a loss object and an optimizer. Who says those should play together? Well, no one does until we tell it. So we want to compile where we say, hey, our optimizer is this object we called optimizer. And our loss is our loss model we call loss. Seems a little redundant, but that's just because we created an object called loss. And we're going to say the parameter loss is equal to our object. That means let's make sure it runs, compiles. Nice. Now we fit. See what happens. Okay. Now we fit our model to our data. Okay. We're going to say model dot fit. Seems a little easier than coding up your own gradient descent and back prop so far, right? Yeah, a little bit. Okay. I heard an exasperated yes. Okay. Now you have to tell it, what are you fitting? We didn't tell it what data we're fitting to. So let's give it our input data, which is X train. Okay. Let's give it our output data, Y train. Okay. And one thing we can tell it is how long we want it to go before it stops. We could have it try to converge automatically and stop when it gets through some threshold, like we did for like a gradient descent. But it's healthy, I would dare say, my friends, just tell it to stop early. All right, just so we can check it. Okay, so we can tell it the number of generations or epochs, loops that we want to do before it stops. So we can tell it epochs. Give it 50. All right. When we're done that, I'm gonna hit go. Are we ready? Oh, epoch 1, epoch 2, epoch 3, 5, 6, 7, 8, 9, 10. Going. Watching it. Okay, now this is not running on some massively parallelized GPU thing, to my knowledge. It's probably just using the CPU, so it could go a lot faster than that. Watching. Is anyone seeing this? Going, look. So this is doing all of the forward propagation, all the back propagation, all the optimizations. This is one loop after the next, after the next, after the next. This is that gradient descent loop. Okay. Oh, we're done. We're done. We did it. It did a thing. Okay. All right. So in essence, what it did is this model object, I'm going to put new code here, this model has now been updated and trained. Inside of it are the values of all the parameters that it just optimized. Okay? Now we can use that model and compare it to the data, to compare it to the data we wanted it to capture. Okay? So what we're going to say here is we're going to create. Okay, let's test the model. So, and plot it against our true data. See how it did. Go from there. Pretty neat, right? All built in. Nifty, cool. All right. So let's get some X test data. Okay. And we're going to say, it'll be np.linspace. We're going to go from between -3 pi and +3 pi. We're going to test it outside of the range that we trained it on. So hopefully it goes bad outside the range. We'll see. So we'll do 3 pi instead of 2 pi. So -3 times np dot pi, and then +3 times np dot pi. And thank you to one of my TAs, DJ, for really working out this example very simply. So he did a great job with this, which is what I was going to say. If this goes wrong, it's his fault. Great. So, all right. So, all right. So that's the test data. Now, the true values, the sine wave values, we would take those test values, put it through our fitting function, our function we want to fit. So we would say our fit function, fit_fn, we called it up at the top of the code, is just taking our X test data and saying, hey, what's the true value of the function, right? Okay. Now, we want to compare it to our model. Okay? Now, let's put the X test data through our neural net to see the test Y data. So Y test. So we'll call it Y test. So let's do forward propagation through this model, putting in all those different X values, and see what comes out of our neural net, and we'll compare it. Y test is equal to model send in X test. That easy. That will do forward propagation on every single value in the X test set. Pretty easy, right? Now let's plot it. Plot the comparison. Okay. Let's say PLT dot plot. Let's plot the X test versus the Y true, the true values. PLT dot, and we'll make that, I don't know, red double line. PLT dot plot. Now let's plot our neural network data. So it's going to be X test, Y test. Let's just make that a black regular line, what it comes up with. Okay, label it X and Y, plot label X, sorry, and plot Y label Y, plot Y label Y. 50. And PLT.title, test, capital test data. Okay. PLT, we'll give it a legend. Okay, how you give a legend? You give it a list. You can say open, close bracket. This is going to be the true data. Then we're going to say predicted, second one. Predicted. Some of you are probably ahead of me. I heard, so I'm guessing they saw what comes out. PLT.show, I see some scared looks. I'm going to run it. Oh, not so good. Not so good. But you can see it's trying, right? You see it's trying to fit? We can do better than that. What if we just added more layers to the neural net? Let's do it. You look scared. What, you don't know if you're scared? You don't know if it's going to work? Oh, well, guess what? Let's find out. Let's find out. Maybe we need more layers. Maybe we need more neurons. If only it was easy to change that. Oh, wait, it's extremely easy to change that. Okay, let's go back to our model. Let's add more layers to our model. Okay? So I'm going to add, you know what, friends? I'm going to add a whole other layer. In fact, I'm going to copy this. I'm going to give 2 more layers. Boom, boom. Scary. Now I'm going to run all. See what happens. Okay, they ran that code. It's going to have to retrain, right? So it's training. Doing 50 epochs. You want me to, so this here, model.fit. Here. There you go. X train, Y train, epochs 50. I just added 2, I copied and pasted 2 more sets of layers. So only 47, am I done? 50? Oh, it's doing crazy things. It's starting a little crazier. Hey, let's make the model more I think the model needs more complicated. More layers. You know what I'm going to do? We can go deeper, or we can go wider. We can add more neurons to the layers. In fact, what's in the middle? Let's fatten out some of those layers. Okay. So let's go do that. Let's go up to our model. And let me know if anyone needs to see any element of the code again. These 2 layers in the middle, I would say go for 50. 50. These 2 middle layers, 50. You see that? We're going to do that. Okay, I'm going to run all again. Okay, let's look at all these parameters, by the way, while it's training. 40, 1,000, 2,500, 1,000, 20. So thousands of parameters. Question? Oh, the 313. I don't know offhand. Question. Okay, where are we at? We're at 47. I'm at 48, 49. I don't know where you all are at. Whoa! Look at that. And I will say, question, yes. Yes. That's a great point. So the question was, it's stochastic gradient descent. That means some of the different numbers you're going to see on mine are going to be slightly different than yours. It's possible you'll get a slightly different result than me. All right? If you're in my optimal control class, you will never see that happen. Our code should absolutely be the same as deterministic. But here, no guarantee. But look. Look at this. It's starting to capture these little wiggles, all with the tan H stance, right? Woo. Right? And also, let's look at the range here. The training data only goes from like -2 pi to 2 pi, from there to there, right? Outside, it's not even trying, right, to get that range. Let's keep playing. I'm going to add another layer. I'm going to add another 50. You know what? DJ didn't even do this. I'm going to put this in the middle. 75. No. Ooh. Just because it looks pretty. I haven't tried this yet. Let's see how it goes. But look, we are playing around with the neural network structure. We're evaluating whether or not it's a good one to fit our data. So much faster, right? Questions so far? Doing okay? That's it. Got it. So it's training across all three, the 300. So it's picking. Yeah. So maybe picking out of the 1,000 data points we have, it's picking a third of them to train off of. If it's stochastic gradient descent, it's randomly choosing them. Okay. All right. Oh, it looks like it ran something. Did it finish? 50, 50, 50, 50, 50, 50, 50. Ooh. Look at this. Question. So the question is, what's the impact of it being deeper versus wider, okay? When you make it go deeper, you're having more and more combinations of activations. So theoretically, as you go deeper, you can get more complex behaviors, okay? But when you go deeper, that extra complexity, maybe that's going to add a ton more parameters, right? So imagine, just real quick, friends, imagine if you had a neural net that had one hidden layer with 10 units on it, right? Okay. Let's say you double the number of hidden units to 20, right? When you do that, you basically double the number of parameters. That's by making it wider or taller, as I'm drawing it here, okay? But if I take those same 10 hidden units and then make it deeper, right? I don't add just 10 more, I don't just double the number of parameters. I have exponentially changed the number of parameters. I now have 10 times 10 parameters on those layers. So it can add a lot more complex interactions, okay? So I'm hesitant to just add a ton of layers. I guess I can, because it's going to add a lot more gradient descent to do. But it's not crazy. It's not like it's taking days to run this. This isn't even using the best of computation to run this. We're probably running this on a CPU somewhere, not even on the GPU. Yes, Angela? Yeah. Yeah. If you have 100, I think you need more. I don't know what the minimum number of nodes you would need per layer, but yes, you could achieve a lot of complexity with just a few nodes per layer and a ton of layers. You can achieve a lot, okay? Now, the exact balance there, I couldn't tell you offhand. It's a deeper question. Your question over there, we'll get back to that. Yes? What if we chose a different activation function? That might be an idea. Maybe something to try at home. How can you find out what activation functions it has? Google. Try them out. See what shape they do. Now, I will say, keeping the last layer linear, good. Okay? Might want to try something, maybe try a ReLU. Anyone remember what ReLU stands for? Since rectified linear unit. It goes like this, and then it goes like an elbow. An elbow. I'm seeing lots of hand gestures, which I assume are all non-profane. Okay, so let's add another. In the spirit of what your question was, let's add more depth. And what was your other question, Angela? let's get back. So the question is, when you want to add more layers versus adding more nodes? This is a more complicated question that I want to get into terribly much today. I'll tell you what I'm doing right now, which is that I'm noticing it just needs more complexity. It needs me to do more wiggles, use a technical term. I add more layers, okay? And if that's not quite doing it, I make them wider. So here, I need some more wiggles. So I'm going to take that 100 layer, I'm going to add another one. What can I say? I'm a crazy person. I volunteered to starve on an island. I can't be that sane, right? So let's add another one, okay? So let's see how that goes. Where's my epochs? We're at epoch 15, 14, 15, 16. I want to fit that curve, gosh darn it. But I hope that you feel empowered now, because literally there's so much you can do with Keras. In the back, are you trying Ray Luz up there? What you doing? No, not trying Ray Luz? It's okay. Trying swish? So it's swish, yeah. Okay. We'll talk more about different types of layers in a future lecture. Definitely want to talk about convolutional neural networks, because they're really important for images. Okay? Where we get, oh, I'm so close. But that's a lot of wiggles, right? Okay. So I'll leave it as an exercise for you all, optionally. See if you can get it to work. Yes. Yours didn't what? Second here. Here, I'm coming over. Apologies. Second. All right, what's up? Oh, yours did it? What'd you do? Let's see your model, my friend. We have a winner here. Someone has won the contest I never defined. Excuse me a second. What you got? Let's see that model. Show me your model. Yeah, you're just taking a screenshot for me, or your own posterity to show your children. Okay. All right. Let's see here. All right. Let's see your model here. Let's see the model. So you did 20, 50, 100, 150, 21. You know what? Maybe I'll run it again. Maybe I got unlucky with the stochastic gradient descent. So, all right. Apparently, people. What was your name? Rhonda. Rhonda has bested me at my own game. Okay. In which case, she managed to get a really good fit with that same layer that I got. So because it's stochastic, let's try running it all again. Random, just random elements, see what happens. Okay? Question? Did you get it perfect? Oh, okay, well, everyone's showing me up today. What can I say? All right. You're all getting perfect. Let's see, why am I not getting perfect here? See, I am at epoch. I want to see what happens when I get to epoch 50. I have the same model, right? You all are using the model here, where I get 20, 50, 100, 150, 21. Taking 40 seconds. So you can see, as I add more to the model, it's taking longer. Now, I say longer. Oh, boo-hoo, we have to wait a minute. And back in the day, okay, yes? Maybe you have to try it again. Maybe to try it again. There are lots of techniques that people use to try to randomly restart to see if it helps, right? So you can see it's a powerful tool, but it's hard to know things for sure. Yes? Ooh, okay, look at that. Sorry, I apologize, Marco, for interrupting you. The sheer excitement of the moment of a functioning model got the better of me. Go on. Yeah, I'll tell you. Yes. So I do want to bring out a couple things. So let me level set. In my excitement, I've forgotten some important points. Okay. Your point was, so one, I'll talk about, Marco is talking about generalization. Look, you can see where our data points begin and end, right? It's beautiful. At least I get something beautiful over here, but over here, I didn't give it training data. So it's not generalizing beyond the training data. Your choice of data matters. Also, I've also taken a few shortcuts here. I told it, don't do more than 50 epochs. It's possible if I let it go for more epochs, more generations, more iterations, it might do better, right? Instead, you could have a stopping criteria, okay? And if you're worried about generalization, we talked about those techniques called regularization. We didn't talk about them much here today, but there are all kinds of tools within Keras to help you. One could be such as early stopping, okay? Let me change the number of epochs. You want to change that? Let's go 50 to 100, and we'll finish off today. Okay? So it's possible that Rhonda, right, had luckier earlier epochs than me, and mine stopped at 50 and it wasn't done yet. What was your name again? William. I'm not trying to detract from your skills at machine learning, but you might have just gotten lucky. You can work with that? All right, sounds good, sounds good. So I'm running there and say, okay, we're executing. Where are we? Or execute epoch number. So we're close to the end here. But I hope you all feel empowered. You can play with these parameters. We could play with the learning rate. Make it bigger, and it might converge faster. Or it could go crazy and not work well, right? But it's pretty darn powerful. All right? Other questions while I wait impatiently for it to train? Yeah? Yes? Okay, what does it say? Okay, I'm going to come check you out here while I wait for my fit function to fit here. Let's see. What does it say? What's the name of the error? Value error.
Been running it.
It's not a valid scope name. So you must be calling something the train name sine wave predictor sequential Keras. Check the Nick, is the link up on the YouTube link? Okay. If you go to the YouTube chat, maybe you might be able to see, compare off of mine, okay? See if it helps. All right. Okay. Oh, it's done. 100 epochs. 100 epochs. Let's see. What did I get? Ooh, baby. Ooh, baby. Pretty good, right? That's all I got for today. Okay? So on Tuesday, we're going to be coming in, and the TAs will be going over your project proposals with you. Okay? Come in prepared to talk about maybe which project you're most interested in, and they can help guide you on that direction so we can move on to the next phase of the project. Thank you all so much.